analyze it. You must have the data into SAS before you can analyze it. There's lots of different types of data. We're going to look at 3 types of data that we can get into SAS. One is when you have a small data set, you can hard code the data into the SAS code. 2, you can import the data from your computer from a CSV file or some other data file. And 3, we're going to import from the internet. So let's go ahead and start SAS. 9.4 English. Make this nice and big. Blank editor down there. So let's begin. Option 1 is going to be hard code the data into SAS. And this is an option that you would use if perhaps you had a small data set or you wanted to share this script across between you and your collaborators. So here's how it starts. Always, when you load data into SAS, you start with the data statement. It's going to be data. Doesn't have to be capital DATA, but I like to capitalize my SAS commands. And then the name of the data set, and we're going to call this tree data for obvious reasons. The next line is your input line. It starts with the keyword input, and then it's followed by every variable that you're going to input. Block is one variable, TRT, MNT for treatment is the second, and growth is the third. This $sign follows treatment because treatment is going to be a character variable. It's not going to be numerical. It's going to be, in this case, an A, B, or C, although any string that you would use. And then at the very end, we've got 2 @ signs. What that means is it tells SAS to keep reading in block treatment growth, block treatment growth, block treatment growth, block treatment growth, block treatment growth until the end of the line. Without that, it's just going to read the first block treatment growth, then go to the next line of block treatment growth. The double ats at the end, it says just keep reading till the end of the line. Now, we don't just have to import the data, we can actually create data as we work within and this is called a data step. It's where we take care of all of our data. So I'm going to define the variable year. It's going to be 1997. So for every single record, the year is going to be 1997. It's a pretty good year. There have been better, there have been worse. I can also create a variable, and I'm going to call it LG growth, and it's going to be the log of the growth value. And growth is in the data set. So in the data step, you can create a new variable all by itself, or you can create a new variable that's based on a variable in the data set. Okay, once you've got that taken care of, you go to the data lines command. And that says, okay, this is going to be the start of the data that we're reading in. These are going to be lines of the data. Alternatively, instead of data lines, you could use the command cards, C-A-R-D-S. That's a throwback to when the data actually was stored on little punch cards. But we're going to use data lines here. And I just typed in the data. Block, treatment, growth, block, treatment, growth, block, treatment, growth. So this is one record. Block 1, treatment C, the growth level is 6.79. This is another record. Block 4, treatment C, with growth of 6.43. Notice there are no semicolons here, but there is one at the end of all the data. Semicolons are very important for SAS. Every line has to have a semicolon on it, unless it's a very special line. And then we're going to end this with run. So I'm going to highlight all of this, and I'm going to run it, or I guess submit. Again, SAS was originally a server language, and you'd be working on your little dummy terminal at your computer. So it always talks about in terms of cards and submitting to your server, and it gives you server times, etc. Now I can either click on this little running person up here, which is submit, or I can hit F3 on my keyboard. I'm going to use F3. Boom. Here's the log of everything that just went down. Line 1, 2, 3, 4, 5, 6. All the data is in lines is associated with a data line statement of 6. And then 10 is the end of it. Then we ran it. I don't see any red here. Red would indicate that there's some error. So everything looks like it worked well. Or did it? It's kind of hard to tell because I really would like to see the data as SAS sees it. And so to do that, in order to print out the data, I'm going to run our first proc. It's called proc print. Proc cancel. Okay, I'm back. But I'm not sure what's going on with the keyboard. Okay, proc is short for process, but it's just proc. And print. And again, you don't have to make these uppercase. I tend to do all my procs in uppercase. Now, proc print says you want to print something out. What do you want to print out? You want to print out your data. And what data do we have? It's tree data. So data equals tree data. And again, end it with a semicolon. Run. And then F3. And then here's results viewer. And this is our data. Block, treatment, growth, year, which is something we created that wasn't originally a part of this data set, and log of growth, which again we calculate based on the growth. So this 1.88858 is just the natural log of 6.61. Notice that up here in the results side, we've got our results. Data set, we can click on that and we get back to our data. So that's method one. It's to hard code the data into SAS. And there's some advantages to that. And the main advantage is, if you look, I can email this to you and you've got this exact same data as I have. Now option two is you're going to import the data from a local file. So let's go ahead and do that option. I'm going to minimize this window. I'm going to go into my H drive. My H drive actually has stat 5013. There's the data set I want to use, Fisher 38. It's a CSV file. How do I know it's a CSV file? Microsoft Excel, comma, separated values file. And if I just want to look at the data, I can double click it. And again, I'm here on my desktop. And it's going to open up into whatever program I have that defaults to opening up CSV files. And in this case, it just happens to be Excel. Consists of two variables. Variable 1 is the sample number, and it's 1 through 4 in Roman numerals. And variable 2 is colonies. Notice again, variables are are columns, records are rows. Okay, so we got sample and colonies as our two variables. Let's get back into SAS. There we go. So now I want to import that data set. So here's how we can do it. There we go. Again, we start the data step with the keyword data. Specify the name of our data set. In this case, it's bact data, which is short for bacteria data. Now the first new part here is the in-file statement. In-file means you're bringing in to SAS memory the file that follows. And again, it's in quotation marks, and and because I'm working on this on the server, this has to be an absolute path, which means it starts with the H colon because it's on my H drive, and it ends up with the name of the data set. It's Fisher38.csv. I have to specify the delimiter is a comma, and that the first observation that I want is in row 2, because in this data set, row 1 was the data was the variable names. So we're skipping over that and going straight to row 2. Second is the input. Notice we had an input back here on when we hard-coded the data. Input was followed by the variable names in order. We're going to do the same thing here. Sample and colonies. Sample, remember, was 1 through 4 in Roman numerals, so it's got to be followed by a $sign. We really don't have to call it sample and colonies, but that's what the data set has it. We might as well. Follow it with a run, and just to double check everything's working correctly, that we got everything in, we follow it up with a proc print. Now again, as before, we could create a new variable here. We could call it year is equal to 1938, which I believe was when this data was done. And we could do log colony, log col is equal to log of colonies. Remembering to end each line with a semicolon. Go ahead and run all this. F3, here's the data. Sample, colonies, year, ln col. So this is 4.06044 is the natural log of 58. Now notice something in SAS. It prints out in a sans serif font, which means it's very difficult to tell what is a lowercase l and an uppercase I. So keep that in mind at times. This could be a lowercase l, or this could be an uppercase I. We do know it's an uppercase I. So keep that in mind when you're using variable names. So that was option 2, importing it from a local file. Option 3 is importing the data from the internet itself. And this is a popular option. You're able to store your data on the internet and have everybody in the group work with that data. This requires a little bit more, one more line. It requires the file name statement. The file name statement will save the URL that you specify to the right and store it in the variable data location. So at the end of running this line, the variable data location will have this string, this URL in it. Notice it's a URL, a full URL. It starts with http:// and then the rest of the address. This line must be run before you can infile this data. Then we start with the data step, call this data stat data. Don't know why, but we'll call it stat data for fun. Followed by the infile statement. Infile, data location, that and that have to be exactly the same. Then again, the delimiter and the first observation. In this file, the first line belongs to the variable names. So first obs will be equal to 2. We're going to skip that first line and just import the data itself. And then again, as with the last, remember the last started with data, then infile, then input. It's data, then infile, then input. Name of the variables, gender, we see, is a character variable. It's going to be M's and F's, or males and females. College is also a character variable. It's going to be CAS, BUS, etc. And those are $signs. They indicate character variable. It's a very strong way of specifying that you're working with categorical variables. And again, we can actually create a new variable. GPA% will just be the GPA divided by 4. We can do just about anything we want. Same as always. All the fiddling with the data takes place within the data step. And then we run it all. If you notice, we had some errors there. So let's go ahead and scroll up on the log and see what those errors were. See if we can interpret what SAS is telling us. This is a good place to actually show you how SAS gives us error codes, or in this case doesn't, and you have to kind of guess what it means. Error, invalid logical name, error in the file name statement. So I know something's wrong with line 24. File name, data location, URL, HTTP, everything looks pretty good. Error in the file name statement. Whatever should we do? And at this point, you realize that SAS really doesn't give you good hints on what's wrong with your code, which is unfortunate. So what I do is I always hop on to Google and Google something like, in this case, SAS file name statement. And then I'll find out, oh, this data location really can't be just any old variable name. It has to be a very specific variable name. That variable name has to be data file. So instead of data location, it's got to be data file. And the only reason I know that is because I went to Google and Googled SAS file name statement. So do that right now. Go to Google and search for SAS file name statement and read up on it. You'll see that there's a lot of help files out there, both within SAS and at other places. Very, very useful. So we fixed it, changed it from data location to data file, changed it here and on the infile statement. Let's go ahead and run it. And here's our data set. ID, grade, gender was males and females, GPA, SAT math, age, college, and GPA PCT, which is percent, GPA divided by 4. Pretty basic right there. So here's what we did in this, and let's go ahead and just finish it off with a nice little quit, just to give us a feeling of satisfaction. So we did 3 things in this little video. Thing number 1 was we showed how to import, how to get the data into SAS by hard coding it. And this is where we did that. Always started with data, then input, and the input told us what the variables were. And when we hard coded the data in, we did it after the data line statement. Option 2 was to import the data from a local file. We started with the data, then in file, and here's where we specified the local file. It is the absolute path, and I have to use the absolute path because I'm using this shared desktop. And then followed by the input. Again, note that the $sign means that the preceding variable is a character variable. And then the third way is to import it from the internet. The new line there is the file name statement. You must start with file name, the word data file, the word URL, and then the actual URL in quotation marks. And then the data step, the in file, the input, etc. So 3 ways of getting data into SAS, and you really do need to have data into SAS before you can actually do anything with the data. I hope this was, oh, and one last thing we did was discover that SAS error commands or error codes are not always that helpful. And so that means that we have to go to Google and do some searching to find out what we did wrong. It's always a good thing is to learn how to figure out what we did wrong. And Google is a great source for that. So I hope this was very helpful. Take care of yourself. I'll see you. Welcome to this quick little video on SAS. Let's go ahead and start SAS. This one actually covers how to do univariate and bivariate sample statistics. So we'll open up SAS as usual, maximize it. Editor. This is where we do all of our typing. First step in any time that you want to analyze data, the first step is to get the data in to SAS. Because if SAS doesn't have the data in its memory, it's not going to be able to do any analysis. So we're going to import this data from the internet. It's going to be the stat grades data set. Remember, keyword file name, followed by the word data file, URL, and then in quotation marks, the URL for the data. It is a CSV data set. Then we start the data step. We're going to call the data set stat data. Follow it with infile, input, and again remember these are the variables in the data file. Gender is a character variable, that's why there's a $sign after gender. College is also a character variable. Categorical variable. We're going to create a new variable called GPA PCT LN, which is just the natural log of the GPA percent. Natural log of the GPA percent. GPA is run from 0 to 4. There we go. And this will load in the data. So after running these, and remember we can either do it by the running person up here or F3 on the keyboard. Let's do it with the running person. Okay, I see no errors in the log. Nothing red up there, so we're good to go. Of course, one thing that we really do want to do is actually look at our data just to make sure that we got it in there correctly. So to do that, we're going to do a proc print. Proc, again, is for process. Print is the actual process we want to use here. Tells the SAS that we want to print something. So what are we going to print? We're going to print the data set stat data. Here's the data set stat data. Now, it may be more helpful that instead of calling this the SAS system, we call it stat data. To do that, we're going to change the title. Title 1 is equal to data colon stat data. So let's run that. It's out of the proper order. Oh, there's no equal sign. Again, note we had that error up there. It said it's not valid. Reminded me that there should not be an equal sign there. Now let's rerun the proc print. Notice up here on the result side, the first time we ran proc print, we got print, which is the proc name, the SAS system. The second time we ran it, after we did the title, we got print, then whatever the title was. Now the title again is up at the top instead of the SAS system. Okay, let's start doing some univariate statistics. Here, the variable the process you're going to use is proc univariate, which kind of makes sense because it's a univariate statistics that you're doing. And what are you going to do it on? You're going to do it on the data, and then run. You run this, and here's what you get. You're going to get univariate statistics for the ID variable, the grade, the GPA, the SAT math, the age, and the GPA percent LN. That's not all the variables. This is just all of the numeric variables. These are just the variables that have numbers associated with them. What are the univariate statistics that you're given? Well, for instance, for the GPA PCT LN variable, you're given the sample size, you're given the mean, you're given the standard deviation, the skewness, the kurtosis, the variance, the sum of all the observations. We're not weighting, so this sum, weights, and n are going to be the same. You're given the coefficient of variation. You're given the uncorrected sum of squares, which is just squaring all of the values and adding them up. You're given the corrected sum of squares, which is just squaring the difference between the value and its mean, adding it all up. Actually, the corrected sum of squares is going to be equal to n times the variance. I'll let you figure out why. You got mean, median, mode also listed here, IQR, range, variance, standard deviation. Skip the test for location. We'll deal with that in a later chapter. We're given the quantiles, Q1, Q3, Q2, min, max, and we're given the 10 extreme observations, the 5 lowest and the 5 highest. A lot of information given here just from one simple line of code, or I guess 2 simple lines of code. And do that for every single variable, but we don't have to. If all we care about is the GPA variable, then we could specify we just want it from the GPA variable. Or maybe we want the GPA variable and the SAT math variable. Notice there's no comma here, and notice this line starts with VAR. Again, that could be lowercase VAR or uppercase VAR. Since it's a SAS command, I like to use uppercase. Let's run that, and we just get univariate statistics for GPA and SAT math. Okay, so that's for all of the numerical variables. What do we do for the categorical variables? It's a new process. It's a new proc. It's proc FREQ. FREQ is for frequency. Data equals stat data. You have to specify the tables. When it was numeric variables or numeric data, we specified var, and it was optional. When it's categorical, we specify tables, and it's not optional. We must specify the tables. We want tables for gender and college. Here's the frequency tables for gender and for college. 45 in the sample were female, 55 were male. That's 45% and 55%. Since gender is not ordinal, the cumulative frequency and the cumulative percent don't make sense. College also is not ordinal, so the cumulatives also don't make sense. 13 business majors, 57 from the College of Arts and Sciences, 11 from the College of Agricultural Science and Natural Resources, 9 from Education, 1 from LASSO, and 9 from Other. Again, the percents for each of those. So the difference is, for numeric data, you can specify the variables you want, but you don't have to. For categorical variables, you must specify the variables you want. So that's all of the univariate statistics. Now we can look at correlations, bivariate statistics. And again, a new proc for you to learn. This is going to be proc core. C-O-R-R stands for correlation. Specify the data. Let's see what we got. Tells us there's 6 variables that it can run correlations on. These are the 6 numeric variables: ID, grade, GPA, SAT, math, age, GPA, PCT, LN. Gives us some simple statistics for each of those 6. And then this table is the correlations. Technically, it's just the first or the top number that's the correlation. So the correlation between GPA and grade is 0.33558, top number. The correlation between age and SAT math is 0.08424. The correlation between GPA and GPA PCT-LN is 0.99144. Those are the correlations between those variables. And remember that correlations are, the order doesn't matter. So the correlation between GPA and grade, 33558, is the same as the correlation between grade and GPA, 33558. The correlation between grade and grade is going to be 1. So it's going to be 1s down the diagonal, guaranteed. And the upper part of the matrix is going to be the mirror of the bottom part, also guaranteed. The bottom numbers, we'll ignore that until we get to hypothesis testing, which will take place later. One last way of comparing two variables. Notice that these were comparing numeric or quantitative variables. We can do it we can do something similar, though not quite similar. We can also do what's called cross-tabulation with the categorical variables. If we look up here, it's proc freq when we're dealing with categorical variables. Tables, gender, and college. Just a space between the two meant that we want a table of gender and we want a table of college. If we do gender times college, then it's going to give us a cross-tabulation of gender by college. So up here we got the number of males and number of females. Here we got the number of business majors, number of College of Arts and Science people, etc. Doing it this way, we're going to get the number of males who are ed, males who are business, males who are College of Arts and Sciences, females who are business, females who are College of Arts and Sciences, etc. So we're able to look at some sort of correlation between these two variables. Now to test that correlation again, we're going to have to wait until later in the course. So there are, in this sample, there are 5 female business majors, 8 male business majors, 3 female ed majors, 6 male ed majors, 5 male others, 8 female Kasners, College of Agricultural Science and Natural Resources. So the whole numbers are going to be the frequency. The numbers right below it are going to be the percent of the entire data set. So female Cas people are 25% of the entire data set. And the frequency is 25, the data set is of size 100, so this is going to be 25 divided by 100 times 100%. The third is going to be the row percent, which means of all females, 55.56 were CAS, belonged to College of Arts and Sciences. Of all females, 8.89 belonged to other. Of all females, 11.111 belonged to business. Of all males, 10.91% were education. So the third number is going to be the row percent. It's going to be of all, whatever the row variable is, that's the percent that belong to the column. Compare that with the fourth variable, or fourth number. This is the column percent. So this would be of all education. So given that the person's in education, of all the education, 66.67% were male. Of all College of Arts and Science, 43.86 were female. Of all business, 61.54 were male. So this is conditional probability. The fourth number is going to be the column percent. Third will be the row percent. So given male, 14.55% were business, as opposed to given business, 61.54% were male. We will cover conditional probability in Chapter 2. You're going to see that it's very important here. And that's it. Univariate statistics. Let's go ahead and just call this quit. Just for the satisfaction, we're done. Felt good. Hopefully this was helpful. Take care of yourself. Okay, we're into SAS. First step when we're doing graphics is to import the data. Makes sense because you can't do much with the data unless it's in SAS's memory. We're going to import the stat grades data set again. Run this. Recall to run it, we can either do F3 or click on the running person. So here's the data that was imported. Should look pretty familiar. Notice up here there's no red, so there was no errors. Okay, so the data's in there. First step, or the next step, let's go ahead and do a bar plot. For all of these charts, categorical variable stuff, function is going to be gchart. Proc gchart. Specify your data. Specify what chart you want. H bar will be for horizontal bar chart. And the variable. Notice college is a categorical variable. Then run. So here's the result. It's a horizontal bar chart. Business, College of Arts and Sciences, etc. The length, or the width, I guess, of the bar is going to correspond to the frequency, or to the relative frequency. There's 13 business majors in that stat class. That's 13%. Ed, there's 9 ed majors, which is 9%. Now one thing we can do to tidy this up a little bit is to get rid of these statistics on the right. To do that, instead of hbar college, we'll just do /no stats. Notice the difference. This is without the no stats. This is with the no stats. Notice the difference. There's no stats. Makes the bar chart a little bit wider. We could also group this according to gender, since that's our only other categorical variable. So group equals gender. Run that. Ooh, it's kind of hard to tell the difference but these first ones are female. So this is the frequency of female business students. This is the frequency of male business students. Female College of Arts and Science students, male College of Arts and Science students. It would be better if there was a bigger space between these two, so let's go ahead and get a space in there. To increase the space, we're going to call it G space. We're going to make it 10. That will increase the spacing between the groups, hence the G in G space. So here's without the G space, here's with the G space. Big space between the males and the females allows you to better see where the break is between males and females. And instead of a horizontal bar chart, we could do vertical bar charts. Horizontal would be H bar, vertical would be V bar. And we can also change the space between the individual bars. Call it space equals 1. So now we got vertical instead of horizontal. We got this space between the groups, the G space. We got the space between each of the categories within the group, which is space equals 1. Female on the left, male on the right. So grouped bar chart. We could also do, instead of frequencies, we could make it percents. Type equals percent. So here it was frequencies. Here it's just percents. Since the data set is of size 100, it doesn't look like there's much of a change. We could also do pie charts. So instead of V bar for vertical bar chart or H bar for horizontal bar chart, it'd be just pi. Go ahead and get rid of all of that. And look at a pie chart. Gives us the level and the frequency of that level, and then graphically puts it into a pie chart. We could also split this by male and female if we want. Same way, group equals gender. But instead of putting the two pies on one graphic, it just splits it over two. So this is for the females, because it says gender equals female, and this is for the males, gender equals males. And this is for everything together. Three, histogram. The bar charts, the pie charts, etc. are all used to illustrate categorical variables. Histogram can be used to illustrate or to look at the distribution of a numeric or quantitative variable. Histograms are found in the proc univariate. Again, it's proc univariate, specify the data, specify the variable that you want the histogram of. In this case, we'll want it of the grade, and then the keyword histogram. Notice every one of those lines ends with a semicolon. Here's what the histogram looks like. Notice that you also get univariate statistics on the variable grade because you're using proc univariate. If you want to overlay this with the normal curve, it's not too difficult. After histogram, got a slash and then normal. And there it is. Now, when you overlay it with a normal curve, usually what you're saying is that you want to test if the variable, in this case grade, comes from a normal distribution. And again, we'll talk about testing later, but this last part does that. It checks to see or provides several tests to determine if the grade variable actually did come from a normal distribution. We'll cover that later in hypothesis testing. That was 3, the histogram. 4 is going to be the box and whiskers plot. This is going to be a tricky one, so you want to pay close attention here. It's proc box plot. So a new process, box plot. Specify the data again. Plot tells you what you want to plot. GPA is going to be the dependent variable. It's going to be the numeric variable. Gender is the independent variable. It's going to be your independent variable. Then specify box style equals schematic. That allows the usual style of box plot where you actually show the outliers. If you leave the box style equals schematic off, the whiskers will run from the minimum to the maximum, as opposed to the lower inner fence to the upper inner fence as usual. So here's the box plot. Oh my goodness, something's wrong here. We've got male, female, male, female, male, female. What gives? One of the quirks of SAS is you have to sort your data before you can do a proper box plot on it. And that sorting is done using proc sort. It's a new process. Proc sort, give it the data, specify what variable you're going to sort by. We're going to sort by gender because we're going to plot our box plot by gender. Now when we run this, we get the box plot that we expected. Female on the left, male on the right. These are outliers for the females. These are maximums. This is a minimum for the males. This is the lower inner fence for the females. Horizontal line, again, is going to be the median. This is Q3, Q1. Here the diamond is actually the mean. So SAS gives you automatically the mean for your box plot, which is kind of helpful. The fifth is going to be the CDF plot. CDF plot uses proc univariate much the same way that the histogram does. So instead of histogram, you'll type in CDF plot. Now if you want the normal overlay, you'll keep the /normal. If you don't, you'll leave it off. Here's your CDF plot with the normal overlay. And finally, the scatter plot. Scatter plot belongs to a different proc. It's not proc G chart, it's proc G plot. Data equals stat data, plot, dependent variable, star, independent variable. And if you want to have different symbols for the different genders, you'll do equal gender. If you want them all to have the same symbol, you'll leave that off. Here's the default scatter chart. Pluses are used. Blue pluses for female, red pluses for male. I guess that makes sense in some way. I'm having trouble seeing the difference between the blues and the reds. It must be my eyes. And the symbols are kind of small, so it's not too helpful, I guess. To make it better, we could make the pluses bigger or change the symbols altogether. And we're going to change the symbols. We're going to call symbol 1, we're going to make it red. Its value is going to be a star, that's an asterisk. And its height is going to be 2. So height equals 2 will make it twice as big than height equals 1. Then symbol 2 is going to be blue, and its value is going to equal a greater than sign. It's interesting. Just so happens that value equals star will give you the symbol for females, and the value equals greater than will give you the symbol for males, which is very natural for this type of plot. Made the females a little bit bigger just to show you that size can be created there. We can do height equals 2 to make the males just as big. And it's much easier to see, or at least this one is much easier to see than the default, where everything seemed to be the same color to me. Now we made it much more obvious, and we really don't even need the legend at the bottom telling us female and male, because we know that this is the symbol for females and this is a symbol for males. I do want to emphasize that there is a really nice little website that shows you all of the special marks that you could have. It's the UCLA website. And that's the end of this. Those were the 6 basic graphics that you can do. So let's go ahead and quit. We quitted. And that's everything. And again, those 6 graphics that we looked at, the first one we looked at was the bar plot, both the horizontal and the vertical. Second was the pie chart. First and the second, the bar plots and the pie charts are used for categorical variables, univariate. Histogram was the third for quantitative variables. Fourth, the box and whiskers plot, also for quantitative. Fifth was the CDF plot, the cumulative distribution function plot. The sixth and final was the scatter plot, which we just finished. Hopefully this was helpful. Take care. Be tests and confidence intervals. These are going to include the t-test, the median test, the Wilcoxon test. Those three are for the population mean or median. It's going to also include the proportions test and the binomial test. Those will be for the population proportion. And the variance test, which will be for, obviously, the population variance. So, let's start SAS. And since we have to analyze data, the first thing we have to do is import the data. So let's go ahead and import the stat grades data file. File name is, as usual, data step. Again, we're going to call our data set stat data. We're going to infile the data file that we defined above. It's comma delimited, so delimiter is a comma. First obs equals 2 because that first row is, since the data set is in canonical form, that first row is going to be the variable names. Then the input line, which has the names of the variables that we're inputting, and these are names of the variables as we want them to be. ID, grade, gender. Remember the $sign tells us that the preceding variable, in this case gender, is a categorical variable. SAT math, age, college, and again college is going to be categorical. In this data step, let's also define the variable term, and we're going to find it to be fall 2014 because that's when that data when the data were collected. And while we're at it, we'll go ahead and create a title for this and do a proc print and run all this just to make sure that we've inputted the data correctly. And remember, when you're running it, you can either do F3 on your keyboard or click on this little running person. We ran it. The results are listed over here in the results window. They're also provided down here in the results viewer. Here's the data. Everything looks like it checked out fine. Term is our new variable, fall 2014. Notice it does not change at all for this data set. That's fine. Since we're doing one population procedures, we really should get to know our data. One of the best ways to get to know our data, especially if we're focusing on the mean or the median of the data, is to create a box plot. If we recall from activity 1B, to create a box plot in SAS, it's proc box plot. Specify the data. Then in the second line, the statement is plot. GPA is your dependent variable. Star or asterisk term. Remember here, term is just fall of 2014. That doesn't change. So this should give us a single box plot. Since we specified box style equals schematic, we're going to get the whiskers going to the inner upper fence and the inner lower fence, and circles will be the outliers. Let's run this. And there's our box plot. We have 3 low outliers. There's the inner lower fence, the inner upper fence. That diamond, again, is the mean according to SAS. This bar is the median, third quartile, first quartile. Looks like it may be slightly skewed negative. We could, of course, determine that using the Hildebrand rule if we wanted to. So, first, it's going to be a one sample t-test. It's a new procedure. We're going to hypothesize that the mean GPA is equal to 3. And so the setup for this test is proc t-test, specify the data, and then for that null hypothesis, which is h0, we're going to say it's equal to 3.0. So this line right here, this part of the line, specifies the null hypothesis. And the next line tells us what variable we want to test. In this case, it'll be GPA variable. And we run these 3 lines, and we get a lot of output. That seems to be SAS's modus operandi, is to give a lot of output. 3 tables and 2 graphics. So let's look at the first table. N is the sample size, mean, this will be the sample mean, standard deviation, sample standard deviation, standard error, this is going to be the sample standard deviation divided by the square root of n, the minimum and maximum GPAs in the sample. Simple sample statistics. Second, it's going to be similar. We're given the mean. We've also got a 95% confidence interval for the mean. We're 95% confident that the mean of the population is between 2.9775 and 3.1731. We're given the standard deviation, and we've got a 95% confidence interval for the standard deviation. We're 95% confident that the population standard deviation is between 0.4329 and 0.5728. That was Table 2. Table 3 gives the results of the t-test. Degrees of freedom is df. This is equal to n minus 1. In this case, n is 100. 100 minus 1 is that 99. T-value is the test statistic value for this data. PR greater than absolute value of t. This will be the two-tailed test, the p-value for that. Because p is greater than alpha, we fail to reject the null hypothesis. In other words, if the t-test is appropriate for this data, then concluding that the average GPA for all students in this population, being 3, is reasonable. We do not have sufficient evidence to say that it is unreasonable. Now note that the t-test requires normality of the measurements. That is, it assumes that the GPAs came from a normal distribution. This first graphic helps to illustrate or to graphically test that. The histogram is from the data. The blue curve is of the normal distribution, and the pinkish, reddish, brownish, whatever color that is-ish curve is what's being observed. So we're trying to compare the normal curve with the kernel curve. If they perfectly overlap, then it's guaranteed that this data came from a normal distribution. They will never perfectly overlap. But is it close enough? And that's really what we're after here, is it close enough? And I don't know. Just by looking at this, I'd say no, it really looks to be heavily skewed to the left. So I don't think it's close enough. I'm not positive, though. If this graphic doesn't do it for you, here's a second graphic. This is the quantile plot of GPA. If the data came from a normal distribution, then those dots should line up along that diagonal line. These dots along this diagonal line. They won't ever perfectly be along the diagonal line, but they should be close enough. Looking at this, it looks like there's a definite pattern here. Starts low, goes high, ends low. This indicates that the data are also left skewed. So both of these indicate the data are left skewed. Now the question is are the data significantly left skewed? And as we talked about in class, one way that we can test that is using the Shapiro-Wilk test. Now to do that, we have to run our proc univariate, and we actually did do the Shapiro-Wilk test, but it was back in activity 1A. It's proc univariate, data equals stat data, and then we add in normal. var GPA because we're testing normality for the GPA variable. So let's go ahead and run these lines. Here's the moments. That should look familiar to us. Basic statistical measures should look familiar to us. Test for location, remember last in 1A I told you let's go ahead and skip over that. Test for normality is the new stuff. Shapiro-Wilk test statistic is W. Its value is 0.938798. The p-value is 0.0002. Because the p-value is less than alpha, in this case it's a lot less than alpha, we reject the null hypothesis. For the Shapiro-Wilk test, the null hypothesis is that the data came from a normally distributed population. We reject that. We conclude the data did not come from a normally distributed population. That means that the t-test is not appropriate. Since the t-test is not appropriate, we may want to use the Wilcoxon test, which is also called the signed rank test. Same null hypothesis we're testing, that the mean is equal to 3 for the GPA. To do the Wilcoxon test, or the signed rank test, use proc univariate, specify the data, add in 2 additional items on this line, LOC count, and our null hypothesis. Here it's mu0 equals 3. For the t-test it was HO equals 3. Here it's mu0 equals 3. Then on the next line specify the variable that you're interested in. Running that, again since it is a univariate procedure, we're going to get a lot of information. The moments, basic statistical measures, test for location of mu0 equals 3. This is the table we want. Remember, we're doing the Wilcoxon test. SAS calls it the signed rank test. Signed rank test is the bottom of the 3. Its value for the test statistic is 657.5. The p-value is 0.0209. Because p is less than alpha, we reject the null hypothesis. And in this case, the null hypothesis was that mu is equal to 3. So if the Wilcoxon test is appropriate, we can reject the null hypothesis. Note that this conclusion is different than the one we had with the t-test. But we concluded the t-test was not an appropriate test because the data were not normally distributed. Here we've got the Wilcoxon test. We reject the null hypothesis, but we really do need to test if the data meet the requirements of the Wilcoxon test, or meet the assumption of the Wilcoxon test, which is symmetry. The data must come from a symmetric distribution. Now how can we do that? Well, we use the Hildebrand rule. Hildebrand rule is the mean minus the median, and the absolute value of that, divided by the standard deviation. If that is less than 0.2, then the data are sufficiently symmetric. If it's greater than 0.2, the data are not sufficiently symmetric. In doing this calculation, we find out that that ratio is 0.222483623. Since that is greater than 0.2, the data are not sufficiently symmetric. The Wilcoxon test is not appropriate. If the Wilcoxon test is not appropriate, we're done. We cannot test the mean of or learn about the mean of the population that gave us this data. That is, unless we actually know the distribution that gave us the data. We don't. But we can start doing some tests on the median. And so the one that we're going to use is the median test, what SAS calls the sign test. It's also a part of proc univariate. In fact, let's have the Wilcoxon test up here and the code for the median test down here. Compare the two. They should be exactly the same. Why should they be exactly the same? Because the code that gave us the results for the Wilcoxon test, or the signed rank test, also gave us the results for the signed test, the median test. So let's run those. Signed rank test was the Wilcoxon test. The signed test is the median test. The test statistic for the median test in this case is 12.5. The p-value is 0.0154. Because the p-value is less than alpha, we reject the null hypothesis, conclude that the median is not 3. And that's it. We have gone through all that. Notice the process we followed. We started with the t-test. We looked at the assumption of the t-test, which was that the data came from a normally distributed population. We tested that assumption. Had the data pass the assumption, we'd report the results of the t-test. In this case, the data did not pass that assumption, so we moved on to the next more general test, which was the Wilcoxon test, or the signed rank test. We looked at the assumption of the Wilcoxon test, which was that the data came from a symmetric distribution. We tested that using the Hildebrand rule. We rejected that assumption. Therefore, the Wilcoxon test, or the signed rank test, was not appropriate. So we moved on to the next more general test, and this one actually was for the median, also called the signed test. No assumptions involved in this. And from the results of the median test, or the signed test, we reject the null hypothesis that the median is indeed 3. And that's the median of the population is not 3. So those were the tests of center. Now let's look at tests of proportions. Proportions tests. Let's examine the gender variable and start out with a typical graphic. This will be a horizontal bar plot of gender. We're not going to include the stats on it. There we go. Female goes out that far, male goes out that far. And for all of these, let's have our null hypothesis be that the proportion of females at Oklahoma State University is 40%. So the first test for proportions is going to be called the binomial test. No, I'm sorry. It's going to be called the proportions test. The code for that, it's proc freq. Not really surprising because we're dealing with categorical variable. Proc freq deals a lot with the categorical variables. Specifying the data set again. The next line is going to be tables gender / binomial p equals 0.40. And this will actually give us the proportions test results. Run that. We're given sample statistics for the gender variable. In this sample, there's 45 females, 55 males. That's the first table. Second table gives us the results of the test, of the proportions test. We'll use this gives us the confidence intervals, so we'll go with the confidence intervals first. We'll use the proportion ASC. ASC stands for asymptotic standard error. And the 95 lower and 95 upper. So we're 95% confident that the true proportion of females at OSU Stillwater is between 0.3525 and 0.5475. The third table gives the results of our hypothesis test. We hypothesized that p was equal to 0.4. Two-sided test gives a p-value of 0.3074. because this is greater than alpha, we conclude that it's reasonable to conclude that the proportion of females at OSU Stillwater is 40%. Pretty straightforward. You get the computer to do the calculations, you interpret the results. The one sample proportions test is actually an approximate test. The exact test is called the binomial test. The difference between the binomial test and the proportions test in SAS is simply the inclusion of a second line, or an additional line, exact binomial. If not for this line, the two pieces of code will look exactly the same. The output is going to be very similar as well. This table is common between the two. This table is common between the two. And most of this table is common between the two. The only difference is when you do the exact binomial test, you also get the p-values for the exact test. These four numbers were from the proportions test. These two are from the binomial test. These four numbers are for the confidence interval for the proportions test. These are for the confidence interval for the exact binomial test. So we're 95% confident that the true proportion of females at OSU Stillwater is between 0.3503 and 0.5527. That's all there is to it. Those are the only two one-sample proportions tests available. The main difference between the two is that the binomial test assumes the data come from a binomial distribution. That may or may not be true. That's completely up to you and the definition of that binomial distribution. The third set of tests that we're going to look at is going to be the variance test. For various reasons, and I'll let you read that in the handout, there is no built-in variance test in SAS. You have to create your own. So that's what we do here. This is SAS programming. This is actually a very simple part of SAS programming. I do not expect you to be able to program SAS, just to use it. And in all reality, a one-sample variance test is rarely going to be done. So, it consists of 3 blocks of code. The first block of code calculates the sample variance and the sample size. Sample variance we're going to call SVAR. Sample size we're going to call N. This line, the output line, actually saves that information from the proc univariate. No print means we're not going to print anything out. So we're just going to use it to save the sample variance and the sample size. The second block uses the sample variance and sample size and your hypothesized variance to calculate the p-value and the confidence interval. These formulas come from the textbook, by the way. This is all done within a data step, and at the end of this data step we're going to have a data set called var test results. And then we print out var test results, the data set that we just created. When we print it out, we're going to get values for the sample variance, the sample size, hypothesized value of the variance, the test statistic, the p-value, the lower confidence level, and the upper confidence level. Highlight, run, and this is what it prints out. Sample size is 100. Sample variance was 0.24312. The hypothesized variance was 0.33. Test statistic calculated was 72.9360. Corresponds to a p-value of 0.045825. And a confidence interval, a 95% confidence interval, ranging from 0.18742 to 0.32809. So we're 95% confident that the true population variance is between these two numbers. We hypothesized it was 0.33, that's just outside the interval, that gives us a p-value of 0.045, which is less than our usual alpha of 0.05, we reject the null hypothesis. We can conclude that, according to the data, it's unlikely that the population has a variance of 0.33. Had we thought or believed or hypothesized that the population variance was 0.25, we could test that by going down here to the var 0 line, change that to 0.25, and rerun the whole set. So for the test that the population variance is 0.25, p-value is 0.88, so we failed to reject that null hypothesis. In fact, every value between 0.18742 and 0.32809 is reasonable as a population variance. And that's the end of this code. This covers all of the one sample tests that you would want to run. And so while we're at it, let's just go ahead and feed in a quit. And we're done. Hope this was helpful. Take care of yourself. See you in class. SAS. So let's go ahead and open up SAS. Again, the log screen at the top, the script screen down here, so it's whatever is in this window is what you'll submit in your appendix. Let's go ahead and load the data. It's going to be the stat grades data as expected. You should be familiar with how to do all of this. I'm going to add one more thing. I'm going to create a variable called gotPass. And we're going to call it gotPass because it's going to indicate whether or not the student passed or failed the course. So we're going to call it gotPass. We're going to say failed for everyone. Okay, now, when does a student actually fail? Well, the student fails if the grade is less than 70%. So if the student's grade is greater than or equal to 70%, then gotPass is going to be value passed. We'll give her a title. Will be grades for stat 4013. Hopefully my fingers start working. We'll proc print it. Just make sure everything's done and end with a run. So we'll go ahead and highlight all this, run it. Again, remember you can either run it by clicking on the little running person at the top or with F3 on the keyboard. And here's what was printed out. Looks like everything's working right. Student got a 56, didn't pass. Student got a 72, passed. So that's one way of creating, or that's another way of creating new variables or new types of variables for your data set. It's a very handy way at times. So let's get a look at our data. Let's go ahead and say for everything we're going to do today, or at least for the means part, we're going to compare GPAs for males and females. So first step, side-by-side box plot. Remember to sort it first. We're going to sort it by gender. We're going to sort it by gender because our box plot is going to be one box plot for males, one box plot for females. And so the form GPA, which is our measurement variable, our dependent variable, asterisk, and then our grouping variable. And as usual, our box style is going to be schematic. that will allow the dots to indicate outliers. And let's run this. And there's our side-by-side box plots. 2 outliers for females. The little diamond is the mean. Looks like the mean and the median for females is a bit higher than it is for males. But the question is it significantly higher? We can also do the same thing or look at the distribution of the data using histogram. So here's how to do histograms. Again, we got to make sure we sort it by gender. It's proc univariate. The variable we're going to use is GPA and histogram. And let's go ahead and break it up by gender. So this is going to give us 2 histograms, one for females, one for males. Here's the histogram for females, the histogram for males. Females look to be a bit more left skewed than the distribution males. We'll find out if that's important. So that was looking at the data. The next step is to actually perform the tests. So we're going to start with a 2-sample t-test. And as expected, it uses proc t-test. Data stated, the variable is GPA. And if we stop here with just proc t-test and var GPA, we're going to get the 1-sample t-test from the last video. But if we specify class as gender, then we're also going to be able to break it up between the 2 genders and get a 2-sample t-test. Output is a lot, as usual. Let's go through the 4 tables. First table gives sample statistics for GPA for the females. The mean is 3.16. GPA for the males, whose mean is 3.00. Standard deviations, errors, mins, maxes, etc. And also for the difference between females and males. Females are, for this sample, or females have, for this sample, an average GPA of 0.1568, higher than that of males. So first table gives us the sample statistics. Second table gives us some confidence intervals. For the GPA for females, we're 95% certain that the population mean is between 3.03 and 3.30. For males, we're 95% confidence between 2.86 and 3.14. We have the same information for the standard deviation. There are now 2 methods for the 2-sample t-test. In the handout, I explain what both of these methods are. I'm going to highly suggest that you only use the Satterthwaite, and I give some ideas to why. So using the Satterthwaite method, the 95% confidence interval for the difference in means is from negative 0.0357 to positive 0.3493. Since 0 is a part of that confidence interval, we cannot state that there is a significant difference or a detected difference between the mean GPA for the 2 genders. Here, this third table is a result of the t-test for both the pooled and the Satterthwaite method. Again, I highly suggest using the Satterthwaite method. Degrees of freedom for the Satterthwaite is 97.579. Test statistic is 1.62. The p-value is 0.1092. Because p is greater than alpha, we failed to reject the null hypothesis, conclude that we did not detect a difference in GPA or in average GPA between the 2 genders. Then table 4 gives us a statistical test for the equality of variances. It's the folded F test. It's one of the available variance tests. The p-value is 0.3504, 3503, because that's greater than alpha. We failed to reject the null hypothesis, conclude that we did not detect a difference in the 2 variances, the GPA variance for males and the GPA variance for females. Now, As with the one sample t-test, there is a requirement that the observations or the data are normally distributed in each of the two populations. Let me emphasize that it's in each of the two populations. Not all of the GPAs are normally distributed, but they're normally distributed for females and for males. Now we can do a normality test, and again I recommend the Shapiro-Wilk test. Notice again that this is very similar to what it was in the last video / handout. The only difference again is the class gender is added. We're specifying that we want to break these up, these normality tests up along the gender. Again, lots and lots of output. Okay, for gender equals female, Shapiro-Wilk test, p-value is less than alpha, so we can conclude that the GPAs do not come from a normal distribution for females. Now if we scroll down for the males, look at the same thing. Shapiro-Wilk test, p-value is 0.0516. That's pretty close. We do not have evidence that the male GPAs come from anything other than a normal distribution. So females were a failure in terms of distribution, males were not a failure in terms of distribution, but both male GPAs and female GPAs have to come from a normal distribution in order for the t-test to be appropriate. Since the females did not, we cannot use the two-sample t-test. So what do? We use the Mann-Whitney-Wilcoxon test. Again, compare this code with its analogy from the last handout. Again, the difference is only the class gender. NPAR stands for non-parametric, one-way procedure. Statistics about the males and the females. Here's the test. SAS calls it the Wilcoxon two-sample test. The test statistic is 2,504.5. The test statistic for, since we were testing difference, it's going to be a two-sided or two-tailed test. P-value is 0.1085. Since p is greater than alpha, we fail to reject the null hypothesis. We don't have evidence that males and females have different average GPAs here. We could also use the Kruskal-Wallis test, which is a little bit less powerful but a bit more exact. That p-value is 0.1078. And even though it's called the Kruskal-Wallis test, this is actually the Mann-Whitney-Wilcoxon test. In this box, they were approximations. This is the exact. So p-value is 0.1078. Again, failed to reject the null hypothesis. Do not be surprised that this p-value for the Kruskal-Wallis test, the p-value for the t approximation, and the p-value for the normal approximation are pretty close. Large sample size means that those three are going to start becoming closer and closer and closer. And there's our paired t-test. So those were the two ways of testing whether or not the means of the two distributions were equal, or the means of the two measurements are equal. The mean of GPA for males versus mean of GPA for females. Let's move on to proportions tests now. And let's look at the pass rate for males versus the pass rate for females. So let's start, as usual, with looking at our data. It's a two-way graphic. V-bar, it's going to be vertical bars. I'm going to group it by got pass. So for those who failed, overwhelmingly male. For those who passed, overwhelmingly female. Just by looking at this graphic, we have an idea that there is a significant difference. The test we're going to use is in some areas called the two-sample proportions test. In other areas it's called a chi-squared test. We'll call it both. Tables, gender, star, got pass. And chi-squared goes after that, CHISQ, because this is a chi-squared test. get 3 tables. This will be our frequency table. This will be for the chi-squared table, and the one that you'll want to look at is just the chi-squared. That's the first row. And if you want to, you can look up Fisher's exact test to see what that's all about. The test statistic for the chi-squared test is 27.2403. That corresponds to a p-value of less than 1 in 10,000. Since the p-value is less than alpha, we reject the null hypothesis, and we conclude that there is a significant difference in pass rates between males and females. We have to go to this table to interpret it even more. Of those who passed, so we're looking at this column, and it'll be the the fourth value, the cull percent. Of those who passed, 63% were female, and 36% were male. If the number of males and number of females are equal, that has meaning. We can look at the row percents, which means that females, of all the females, 93.33% passed, and of all the males, 43.64% passed. That's a little bit more meaningful in general terms. The column percents really do require that the number of males and number of females are equal. The row percents do not. And the last test that we're going to look at is the variance test. We're going to compare the variance of males versus the variances of females' GPAs. And we've actually seen this test already. It's back in the Proc t-test. This is that fourth table, the equality of variances test. Here, SAS wants us to use the folded F test. The test statistic is 1.32. The p-value is 0.3503. Because p is greater than alpha, we fail to reject the null hypothesis. We have not detected a difference in the variances of GPAs between males and females. Now, honestly, variance of GPA, not that important, but variance is also a measure of risk in the stock market. So instead of thinking of male and female GPAs, think of price of IBM versus price of Apple. You would generally, all things being equal, you would generally want the lower varianced stock. Here we're detecting that there is no significant difference in the two risks. Therefore, IBM, Apple, doesn't matter in terms of risk between the two. So, I hope this was helpful. Again, take care of yourself. I'll see you in class. This really is just an introduction to it. So the first thing we've got to do, as usual, is import the data. We're going to use the usual data set, the stat grades data set. And again, click on the little running person up here, or F3 on your keyboard. Looks like everything came in correctly. Let's do a proc print. Just to double check, just to get a feel for the data. And remember, you always want to get a feel for the data. Observations and identifier, grade, gender, GPA, college. One thing you'll notice is that there's only one lasso person in this group. So if we're trying to determine the effect of college on grade, or see if there's different grades for different colleges, having one person from lasso is not going to give us enough information about lasso. So let's take lasso and bundle it with all the other group. Now let me show you how to do that, to recode lasso into other. So we'll go back up here to the data step. So what are we going to do? We're going to see which of those have college equal to lasso, and then change those college to other. That's all we're doing. So there we go. So if the college value is lasso, then we're going to make the college value other. If the college isn't lasso, then it's not going to do anything. And notice down here, the last so person is now an other person. So we just recoded part of our data. That will be very useful in the future for you and all of your data analysis. There are many ways of doing it. This is just one of them. Okay, get to know your data, so let's go ahead and look at some graphics. Histogram, we're going to do histograms by college, so we're going to have 5 histograms. That doesn't look right. What's wrong? It's not sorted in ascending sequence. That's right. We have to sort by college before we can do a histogram. So it's just proc sort. Now we've got it. So here's business. Here's arts and sciences. That looks really normal. Here's College of Agricultural Science and Natural Resource. Education. Other. That one looks pretty normal too. We could also do box plots. Side-by-side box plots. Get a little feel. It looks like the average for Kasner and Ed are higher than everything else. Oh, this is GPA. We're looking at grade. So let's rerun those. There we go. Looks like Kasner's average, which is the diamond, is much higher than any others. Looks like business is much lower than all the others. So already we have an idea that perhaps there is an effect or a differential effect of college on grade. That Kasner students seem to do much better than business students. Well, let's figure this out. Let's do one-way ANOVA. And it's called one-way ANOVA because we have one independent variable. It's proc GLM. GLM stands for Generalized Linear Models. Give it data. Specify the class. And class, again, is the categorical variable, college. And then the model. The model is going to be the dependent variable, equal sign, independent variable. Or in this framework, it's going to be the measurement, equal sign, grouping variable. And then we run it, and then because of some internal features with the GLM process, we're going to have to do a quit immediately after. I guess have to is not the right word, but that's all there is to it. Here's the results of the GLM procedure. Here's the first page. Tells us there are 5 levels in the college: business, arts and sciences, Kasner, education, and other. There were 100 observations that were read, and we were able to use all of them. This is the usual ANOVA table. The source, the degrees of freedom, the sum of squares, the mean square, the F value, all those we calculated in class, and then the p-value. P-value is less than alpha, therefore we reject the null hypothesis. Again, in this case, the null hypothesis is that all the means are equal. These two tables give different types of sums of squares. Since we're doing one-way analysis of variance, these will give absolutely no additional information. If you move on to two-way and above analysis of variance, these will give additional information, but since we only do one-way in this course, we'll have to postpone discussing that until Statistics for Experimenters 2. Here's the histogram, box plot, side-by-side box plot. Again, the diamonds are the means, the horizontal bar here is the median. This also gives the test statistic. F is 10.18. F is 10.18. And the p-value, in this case, again, less than alpha. So we've now concluded that, assuming analysis of variance is the correct procedure to use here, we're able to conclude that at least one of the 5 colleges has a different average grade. So let's test the assumptions. Remember that there are two main assumptions above and beyond the usual assumption of independence. The first is the assumption of normality. We remember how to do that from earlier. Sort it by college, proc univariate, and then give it normal. And that will give the normality tests, several normality tests. Recall that the one that we're going to be using will be the Shapiro-Wilk test. Also note that there's 5 tests being performed here, one for each of the colleges. Therefore, you should multiply the p-values for the Shapiro-Wilk test by 5. Here's the p-value for the Shapiro-Wilk test for College of Business. We don't have evidence that it's non-normal. The next one is for College of Arts and Sciences. There's a p-value 0.3, multiply that by 5. That's also greater than alpha, therefore no evidence of non-normality for the College of Arts and Sciences. College of Agricultural Science and Natural Resource, multiply that p-value by 5, again because there's 5 normality tests we're running. There's no evidence of non-normality for Kasner. Education, 0.3477 times 5, also greater than alpha. And finally, the other group, 0.9155, again, greater than alpha. We multiply that by 5, greater than alpha. So no evidence of non-normality, which means that this model and this data pass that assumption test. The other assumption test is equality of variance in the populations, in the 5 populations here. There's many ways of testing for equality of variances, what's actually called homogeneity of variance. We're going to use the basic Levene test. To do the Levene test, notice that the first 3 lines again are just the same as the proc GLM from above. We're really just adding this new line. The means line states the grouping variable. HOV test is homogeneity of variance test, and we're going to have SAS run a Levene test. Levene offers several types. We're going to use type equals square, so it's going to be the squares of the measurements instead of the absolute values. We'll run that. Output from the GLM procedure starts way up here. 5 levels, that's familiar. This is also familiar from the last GLM proc that we ran. This as well. Here's the new line. Levene's test for homogeneity of grade variance. So it tells us immediately that the null hypothesis is that the variances are the same. Homogeneous variances are the same. So we look to see if we can reject that null hypothesis. There's the p-value, it's 0.8. 0.8 is greater than 0.05, which is our alpha. Therefore, we fail to reject the null hypothesis. Therefore, this data and model pass this assumption test as well. So it passed the normality tests, and it passed the Levene homogeneity tests. So it passes all of those assumption tests, which means that analysis of variance actually was the correct procedure, or we are allowed to use it, and we're able to conclude that at least one of the means is different from the others. That's all we're able to conclude right now. One of the means is different from the others. We don't know which means. We just know that at least one, could be 2, could be 3, but at least one is different from all the others. All that work, and that's all we're able to conclude. That's fine. The next step is to determine which is different. And not just which is different, but which is different and in which way. How are we going to do that? Again, it's the proc GLM. These 3 lines are going to be exactly the same as before. We add in this new line. Means. College is going to be the categorical variable. And then after the slash is going to be the multiple comparison test we want to use. We're going to use the 2-key HSD test. When we run those lines, we get a lot of output. Let's see, where do we start? We start back here. Same output for the GLMs, same output for the proc GLM. Nothing there is different. Here's the new part. Tukey studentized range HSD test for grade. Specifies that alpha is 0.05. Error degrees of freedom, error mean square, we calculated those in class. Critical value, we also calculated in class. That was a lot of work. SAS does it all for you. But the drawback is you've got this incredibly large table that you have to interpret. So how do you do that? The way that I do it is I look for the stars. The stars indicate that the difference is statistically significant at the 0.05 level. In other words, for this one, we know that Kasner minus Cass is significantly different from 0, which means, since the difference actually is positive, Kasner has a statistically higher average grade than Cass students. Since Kasner minus Cass is positive, Kasner is greater than Cass at a statistically significant level. And since that difference is 11.391, I'd say that's a practically significant level as well. Kasner is also greater than other. Kasner is greater than business by a whole lot. Kasner is not significantly higher than education. No stars here, therefore this difference is not significantly different from 0. There's no detected difference between the average Kasner grade and the average education grade. So Kasner is not significantly different from education, but it is higher, significantly higher than arts and sciences, other, and business. We know from here that education is significantly higher than business. We know that arts and sciences is significantly less than Kasner, which we knew from above. We know arts and sciences is significantly higher than business. Other is significantly lower than Kasner, which we also knew from above. And business is significantly less than every other college. So, here's what we can conclude from this. Business is significantly less in terms of average grade than all the other colleges. Kasner is significantly more than all the other colleges in terms of average grade, except for education. And there's no significant difference between the education, arts and sciences, and other. It's kind of interesting. Business the lowest, Kasner the highest, except it may not be higher than education. So that was multiple comparisons. And we can do multiple comparisons if we reject the null hypothesis of analysis of variance. If after we do analysis of variance and the p-value is greater than alpha, we conclude that there's no detected difference amongst the several subpopulations. If we've failed to detect a difference, it doesn't make sense to then go and look for a difference by doing multiple comparisons. Finally, remember there were two assumptions for analysis of variance. There's the equality of variances and the normality. If any of those are violated by the data in the model, you can't use analysis of variance. You'll use what's called the Kruskal-Wallis test. Here's what you would run. This looks very familiar to us. It's very similar to what we've done with the two sample tests. In fact, I think the code is exactly the same. The only difference is the class variable, college in this case, has more than 2 levels. So SAS knows to run a Kruskal-Wallis test on it. P is less than alpha, reject the null hypothesis of equal means, and therefore conclude that at least one of the means is different from the others. Can we do multiple comparisons with Kruskal-Wallis test? Absolutely. And I encourage you to take the nonparametrics course where we cover how to do that. Well, that takes us to the end of this video. I hope this was helpful. Take care of yourself. See you in class. has to do just that. So let's go ahead and begin by importing the usual stat grades dataset. Nothing special. File name, data step. Don't need to change the date at all. Of course, we should probably determine if we import it correctly. And do a proc print. Let's run it and make sure everything looks good. No errors at the top, and it's going to pop up with the HTML page. Everything looks fine. Notice we didn't change the other. We didn't change the lasso to other. We're not studying the colleges, so we don't need to do that. If we were studying the colleges, we may need to do that in the future, but we're not, so we don't. As always, let's go ahead and plot our data. I'm going to do a really massive block of code here just to show you some of the strengths of SAS in its graphing. It's kind of odd. Up until recently, saying SAS is good at graphing would get you laughed at. But I'll go ahead and highlight all this and run it. Let's look at the graphic we got. X-axis, this will be the independent variable. Here's the initial grade point average. Y-axis is the dependent variable, course grade earned. We've got this broken up into red female figures for the females and blue male figures for the males. If we look, there looks to be a positive correlation between the two. I'm not sure that it is statistically significant, but it looks like there is. Notice that both the initial grade point average and the course grade earned start at 0, and it starts exactly at 0. So how did I get this to happen? Let's go through this code a little bit line by line. These two lines look familiar from 1b. We define two symbols. Symbol 1 we're going to make red, make it a little bit bigger than usual, 75% bigger than usual. And we're going to give it the value star, which actually is the female figure. And we're going to define symbol 2 as blue, make it also 75% bigger, and that'll be the value is equal to the greater than sign, which is the male figure. Symbol 1, symbol 2, so when we do the plotting, and down here we set it equal to gender, so it's going to split it up into the two genders. Symbol 1 will correspond to the first gender, symbol 2 will correspond to the second gender. Why is female the first and male the second? The alphabet. These two lines are going to be new. They define two different axes. Axis 1 we're going to define as being ranging from 0 to 100 and marks every 10. And we're going to actually start it at 0. We're not going to have any padding on the top or the bottom. Axis 2 is going to range from 0 to 4. We're going to have marks, major marks every 1, and again it's going to go directly to the edges. Offset is 0. We're going to utilize those two axes in the plot statement. The vertical axis is axis 1. The horizontal axis, that's H-axis, is axis 2. And the next thing that you'll notice is the legend command. Here we're just saying where we're going to put the legend. The position we're going to place it will be the top center and on the outside of the plot. And we're going to use that in the plot statement. Down here we're going to define where the legend is. Now the proc gplot also came from SAS 1b, and this part came from SAS 1b. What the no frame does in the plot statement is gets rid of the box around the plotting region. Now if you notice, I actually have initial grade point average stated down here and course grade earned stated up there and student gender stated up there. If we didn't, this would just be little g, little p, little a, and little grade and little gender. To make it a bit more reader friendly, we're going to say, okay, that GPA is actually going to be replaced by initial grade point average, grade is going to be replaced by course grade earned, and gender is going to be replaced by student gender. So that's what all those parts mean when you put them together. It produces this really interesting graphic. I think it's worth the extra steps. Okay, now we've looked at it. We do think there may be a correlation. If there is a correlation, it's positive. As the initial GPA increases, the course grade earned also increases. Let's go ahead and test that. We're going to use proc core, which we saw back in 1A. Proc core, specify the data. We're going to specify the two variables that we want to find the correlation between. And Fisher is going to allow us to get some more statistics off of it. Highlight, run. Here's the one-page output. Two variables, grade and GPA. We have some summary statistics for both of those two variables. We have the correlation coefficient based on Fisher for the two variables. Grade and GPA have a correlation of 0.33558. The p-value for the test, that correlation is actually 0, is 0.0006. Since that is less than alpha, we reject the null hypothesis, conclude that there is a relationship between these two variables. We have a 95% confidence interval from 0.147 to 0.498. We're 95% confident that the true relationship between those two is between those two values. Again, since the p-value for the test of h0 rho equals 0 is less than alpha, we know that it is not 0. Back in 1A, we talked about the correlation and looked only at the value of the correlation. We didn't talk about that test statistic or the confidence intervals because it didn't make sense. We didn't understand those terms back then. Now we do. So it's kind of nice to go back over some things that we've done in the past and look at it with new eyes because we've learned stuff since then. So we've got a significant correlation between the two, but we're not exactly sure. I mean, that's good information, but we'd like to go to the next step. We'd like to model that dependent variable, the grade earned in the class, using the independent variable, the initial GPA. To do that, we'll use linear regression. We've seen this before. Proc GLM, state the data, the model. Grade is the dependent variable, the y variable. GPA is the independent variable, and we could just run it. CLParm gives us confidence intervals for the parameters. Where have we seen proc GLM before? We've seen it when we were dealing with analysis of variance in the last video. The difference between this use of GLM, proc GLM, and that use of proc GLM is this use of proc GLM is missing a line. There is no class line here, or class statement, because neither grade nor GPA are categorical variables. So let's run this. The output should be pretty familiar to us, since we've already seen proc GLMs. Page 1, number of observations used. Spend an entire page on that. Page 2 is the big one. Here's the ANOVA table. P-value is 0.0006. Since p is less than alpha, we know that this model does tell us something about the relationship between the dependent variable and the independent variable. If this p-value were greater than alpha, we'd say that this model was not useful. Next table gives us the R-squared, the coefficient of variation, and a couple other things that are useful for a different stat course. We've got the two types of sums of squares. If we had more than one independent variable, this might be useful. We don't. Notice that these two tables will give us exactly the same information as the first row of the top table, only because we have one independent variable, one dependent variable. This table is the new table. This gives us parameter estimates. The estimates are here. This is B0. It's the estimate for beta naught. And this is B1, the estimate for beta 1. There's the test statistics, the p-values. Both are less than alpha, therefore neither of these are 0, and we got confidence interval. If we didn't have the CL parm, we would not have these confidence limits. We also have the graphic, nice little basic graphic. The line is going to be the line of best fit. The equation for this line of best fit is 46.415 plus 8.4202 times x is equal to y. B0 plus B1x equals y. The shaded area is the confidence interval or the confidence band for the line of best fit. Stat 4043 discusses that. And the dashed line gives us prediction limits, which are also discussed in Stat 4043. So based on that, those two tests, we know that there is a relationship between these two variables. In fact, we were able to determine what that relationship was. These two numbers give us the line of best fit, which means for every 1 increase in GPA, the expected value of the grade in the class goes up by 8.42 points, on average. Now if we look back at our plot, see if I can pull up the plot. If we look back at this, there seems to be some difference between females and males in terms of course grade earned. It seems as though females did better than males. So let's add gender as one of our independent variables. That's called multiple linear regression because we have more than one independent variable. Again, since we are doing this by gender, we need to sort it first. ProcGLM by gender means that we're going to first fit the model with females, then fit the model with males, and then we'll be able to compare the two. Everything else is exactly the same as the simple linear regression above. Go ahead and run that. Scroll to the top. Okay, GLM procedure for females. 45 females read, 45 are used. P-value for the model is 0.0071. Model is useful. Scroll down to the parameter estimates. 53.19 is the estimate for beta naught. 8.626 is the estimate for beta 1. On average, for every 1 increase in GPA for females, the grade goes up by 8.62. Both of these are statistically significant. That is, that they are different from 0. For the GPA, that test actually has some meaning. For the intercept, usually it's not, from a science standpoint, it's not interesting if the intercept is different from 0. But almost always it's interesting if the slope or the effect is different from 0. So that was it for females. Let's scroll down and see what happens with males. 55, 55. P-value is 0.0763, which means this model doesn't really do much for the males. We do still have the our estimate of beta naught and beta 1. On average for this sample, as you increase the GPA by 1, the grade goes up by 4.67. But if we look at the p-value, that p-value for the effect is greater than alpha, which means that it is not significantly different from 0, meaning that we cannot conclude GPA has an effect on grade for males. Scrolling up, we do see that it has an effect on grade for females. It just does not have an effect on grade for males. In fact, we're 95% confident that the effect is somewhere between a -1/2 and a positive 9.9. In other words, as the GPA goes up by 1 for males, it could actually go, the grade could actually go down by 0.5 points, or it could go up by about 10 points. It's rather interesting. It's rather contrary to what you may think, too. seems as though the GPA, as GPA goes up, the grade should go up. Now, notice that what I haven't said here. I have not said that increasing GPA causes the grade to go up. I'm just stating that there is a very strong relationship between the two. It is quite likely that there is a third variable, what's called a confounding variable, that causes both GPA to go up and grade to go up. Now, if you sit and think about it for a moment, you'll think, that makes sense. Maybe work ethic would cause the GPA to go higher and the grade in stat class to go higher. Could be natural gifts that would cause both to go up. Not sure. That's for a different analysis. For this analysis, we just looked at GPA and grade. And we did all this using SAS. Notice the important processes. Proc core gives us the correlations. Proc GLM allows us to do the regression. I really hope this was helpful for you. Enjoy yourself. Bye. Usual stat grades data. We are going to need to use a dichotomous variable, so we're going to use got_pass. It's going to be defined as whether or not the student's grade was greater than 70. Also, we're going to be dealing with the college variable, so we need to recode that student who was lasso into other. And let's proc print it just to make sure we did it correctly. It looks like everything's working. Got_pass is there, college. We're all good to go. And so the next thing to do, as always, is to learn about your data, to see your data, to plot your data. So we're going to look at gender. So the next question here is gender across the colleges. This would be an interesting question. Somebody may hypothesize that certain genders prefer different colleges over others. So to do this, we'll do a proc G chart. It's going to be a horizontal bar plot of gender. We're going to group it by college. And we're going to put spaces between the college groups of size 5. Run those. And here's what we get. It looks like overall there's not much difference between males and females in each of the colleges. There could be, but it doesn't look like there is much of a significant difference. Looks like maybe males over females in College of Business, and maybe females over males in Kasner, but I'm not exactly sure that those differences are statistically significant. To test if the distribution of genders across the different colleges is equal, we use a chi-squared test of independence, which will be part 3. But on the way there, we can go ahead and look at the distribution of the colleges. Perhaps we want to look at the distribution of the genders, hypothesize about those. So let's look at the distribution of the colleges now. Since we're looking at the distribution of the colleges, we're not grouping by anything at this point. That'll be the code. Looks like arts and sciences has a lot of students, which doesn't really surprise us because in most colleges, most universities, the College of Arts and Sciences is the most populous. But we could test the null hypothesis that the proportion of students in business is equal to the proportion of students in arts and sciences is equal to the proportion of students in Kasner is equal to the proportion of students in education is equal to the proportion of students in others. That is, a student is equally likely to choose any of those 5 colleges or groupings of colleges. Since we're testing if the student is equally likely on this one categorical variable, we're going to do a chi-squared goodness of fit test. And it's a proc freak because we're dealing with the categorical variable. Tables, college, we saw this back in 1A. The new thing is /chi-sq, which stands for chi-squared. And that tells SAS that you want to do a chi-squared goodness of fit test. It knows it's a chi-squared test because you told it chi-square. It knows it's a goodness of fit test because it is a single variable. Since we specify nothing beyond the chi-sq, then it's going to, by default, test equal probabilities. We'll run this. we get this output. First table gives us the raw frequencies, percents. The second gives us the result of the hypothesis test. This is a chi-square test for equal proportions. P-value is less than alpha, therefore we reject the null hypothesis of equal proportions. Test statistic is 86, degrees of freedom is 4 because there were 5 groups. This graph shows the deviations from equal probabilities. Arts and sciences, very, very large deviation, positive. That is, they have many, many more students than they would if the null hypothesis were true. And the other 4 colleges have fewer if the null hypothesis were true. But because p is less than alpha, we reject the null hypothesis and conclude that the colleges do not have students in equal proportions. It doesn't surprise us. Arts and sciences tends to have 6 times the students of any other college in most universities. So to test that, let's hypothesize that arts and sciences does have 6 times more students than any other college. Still proc freak, still tables of college, still chi-sq, but the new part we're adding in is this. The testing proportions is 0.1 or 10%, 0.6, 0.1, 0.1, 0.1. These have to add up to 1. The order is based on the table. Business first, arts and sciences second, Kasner, followed by ed, followed by other. So we're hypothesizing business is 10%, arts and sciences is 60, Kasner is 60, ed is 60, other is, 10%, 10%, and other is 10%. And we would make this null hypothesis just by from our experience that arts and sciences tends to have 6 times the students as any other college. We're running it. Running it if I push the right button. There we go. Frequency distribution, chi-squared test. It's a test for the specified proportions. The test percent is given up here, 10%, 60%, 10, 10, 10. The p-value is greater than alpha. Therefore, we fail to reject the null hypothesis. This distribution of percents is reasonable given our data. Notice I did not say this is the correct proportion distribution, only that this distribution is reasonable given our data. And while it may look like business has a very large deviation, compared to what we had under arts and sciences was off by 2 on this relative deviation. On these, business is only off by 0.3. So it's off by even less than 1/6. This model is a much better fit. These proportions, these hypothesized proportions, fit the data much better than did the equal proportions. Again, I have to emphasize, we are not saying that these proportions are the correct proportions. We're saying that they're reasonable given our data. Statistics is usually about what is likely, not what is possible. Think about that for a moment. Let's move on to tests of independence. Tests of independence happen between 2 variables. Let's go ahead and look at gender versus college. I'll create a nice little cross tabulation. It's going to be a proc freak. Tables, notice there's no slash or anything after it because we just want those cross tabulations. Here's a cross tabulation. Refer to 1a as to how to read these numbers. Now, to test if those 2 categorical variables are independent, what do you think we're going to do? Yes, we're going to add on that slash and chi-sq. This gave us a cross tabulation up here. This gives us the test for independence. Notice the only difference is the slash and the chi-sc. Here's the cross tabulation again. Here is the results for the test of independence between the two variables. The one I want you to pay attention to is the chi-squared test statistic. The value is 4.2674. In class we saw how to calculate that. The p-value is 0.3710. Because p-value is greater than alpha, we fail to reject the null hypothesis. We cannot conclude that there is a relationship between these two categorical variables. Another way of saying that is we cannot conclude that different genders choose the different colleges at different rates. That the proportion of males to females in arts and sciences is not significantly different than the proportion of males to females in business, or in Kasner, or in education, or in the other group. We don't have evidence that females choose one over the other, or males avoid one over the other. Another way of thinking of this is, if I ask you to predict somebody's college, and I'm just telling you this is a college student, your prediction would most likely be College of Arts and Sciences. 57% of our sample chose Arts and Sciences. And now I say, okay, given that the person is female, what's the most likely? Given that the student is female, well, we just showed that given that additional information gives us no new information in terms of predicting college. It's just as useful for predicting college as the number of toes on the left foot. The two variables are independent. Okay, what may be interesting, or more interesting, is not gender versus college, but remember this is classroom. These are students in my class, and we can also look at whether or not students pass at a different rate in different colleges. So instead of gender by college, I've got pass by college. Here's the cross tabulation. Chi-squared test is 0.0053. P is less than alpha. Reject the null hypothesis. Therefore, these two categorical variables are not independent. They are not independent, which means that the pass rate differs across the colleges. The pass rate differs across the colleges. Or technically, at least one college has a pass rate that differs from the others. That really doesn't surprise us. If we look at the cross tabulation, almost 77% of the business students failed to pass. Almost 70% of the arts and science students passed. 91% almost of Kasner students passed. So just by looking at the cross tabulation, it doesn't surprise us that we're going to conclude that there's a differential pass rate. Not at all. Kind of makes you think, why do business students pass at a much lower rate than the other colleges? But that's a question for science, not statistics. For statistics, we just said there's that differential pass rate. Science needs to come along and explain why. And that's the end.